Lesson 25, the speed of light, is one of my favorite lessons of the year. It goes over how certain scientists try to determine the speed of light, and eventually we did. We actually have a very accurate value for the speed of light. It's just under 300,000 kilometers per second, or 300 million meters per second. It's super fast. Just remember that if Edmonton is 300 kilometers away, a beam of light will travel to it and back 500 times in a single second. 500 times a second. So it's a huge number that's even hard to imagine, and that it takes 8 minutes from the light of the sun to reach the Earth. And we are presently looking at stars that it takes 14 billion years for their light to reach us. So just to try and emphasize the magnitude of this, or the scope of this universe that we are part of. Anyway, here we go. We got Galileo was the first guy who tried it, and valiant effort, but his method for measuring the speed of light was not going to yield anything significant. He used lanterns on a couple of hills that were several kilometers apart, and tried to open one lantern and time how long it took the light to get over. Anyway, because light travels so fast, there's no way he was going to get anything remotely accurate. So good try, Galileo, but no can do. Ole Roma did use this method to measure the speed of light, and he came up with a pretty good value. And he was looking at Jupiter and the moons of Jupiter. I think specifically Io. Io is a moon of Jupiter, and Io goes around Jupiter, and from Earth you can see Io going eclipsing, going in front of Jupiter. And that's obviously happens on a regular basis, happens every 24 days or whatever number it is. But of course, Jupiter and the Earth are not always the same distance away from each other. So over here we have the Earth, and we have Jupiter, and then later on in the year, they're further apart from one another. So what he did was he used this eclipse since he knew that the moon going around Jupiter, since he knew this was occurred on a regular basis, he could measure. But when Earth is further away over here, obviously the light is going to take a longer amount of time. So he knew what the time delay between this eclipse was from this situation here to this situation here. And he knew the distance between them, so he just very simply used this formula here, velocity equals distance over time, and that's how he calculated the speed of light, which was pretty darn ingenious for that time. And then we come on to the more intricate ways of measuring the speed of light. We have Fizeau and Foucault, and Fizeau used a tooth mirror. And you should really Google. Oh, before you do that, you should probably go watch this video on the history of the speed of light, because it kind of goes over all this stuff. It's right there on YouTube, measuring the speed of light in history. It's only 3 minutes. Go watch that. Then come back to this, and we're back to Fizeau and Foucault, and they use the tooth mirror. And you might want to Google a video on those. It's a tooth mirror. To find out a toothed gear, and with a mirror, and the light would go through the gear, hit the mirror, bounce back, and only when it was revolving at a certain frequency could you see the light. So Fizeau got to within about 5%, and then along comes Foucault, another French physicist, and he used a mirror. And this is pretty much this is the one that we study mainly. This is Michelson, an American physicist, Albert Michelson. He used the same kind of principle, and this is how he did it. And this is the one that you should know. This is super, super cool. Remember, this is the end of the 18th century. So well over, or just over 100 years ago, they were doing this kind of stuff, trying to measure the speed of light with none of the technology we have today. Here's his apparatus, and it's brilliant. So here's your light source, the sun. And here's a mirror. This is an octagonal mirror. In other words, octagonal. So it has 8 sides. And your mirror can have, 6 sides, 12 sides, 10 sides, however many you want. He uses an 8-sided mirror, and So if the mirror is just stationary and you shine the light hits the mirror, and then it goes to another mirror down here, which is a long distance away. We're not talking about 5 meters away. We're talking about 30 kilometers away. So it hits the mirror here, bounces back, hits this side of the mirror, and you observe the light right here. All right? But let's say you start to rotate the mirror. So you're rotating it in this direction. If you're rotating the mirror, then this cycle will only be completed if the mirror makes 1/8 of a turn in a very specific time, right? Because if the mirror, let's say the mirror turns, so the light hits here, and the mirror this time is oriented this way. So 1, 2, 3. Oh, this is awful. This is awful. You get the idea. The light's going to hit the mirror, and it's going to bounce, and oh, it's going to hit the mirror here, and then bounce back, and it's not going to hit the other mirror, or it will bounce back and hit the other mirror, wherever that is, and not reach the light source. So hope I did a terrible job there, but I hope you get the idea. The mirror has to turn 1/8 of a turn in a very specific time interval for it to make this cycle so that you can see it. Okay, so that's with an octagonal mirror. It has to make an 1/8 turn in a very specific time, and then this cycle will be completed. So the light hits the mirror, and then it turns, and then by the time it's made 1/8 of a turn, the mirror is in this orientation again, so that it makes that cycle. Wow, that's a mess. Okay, watch a video on this. It's super cool, super cool. So that is how Michelson determined the speed of light. And here's an example. This is, if you're writing your diploma, you would get an exam question. Usually you get a question, a Rome question or a Michelson question. And here's how a Michelson question works. So you've got Michelson did this experiment, and the curved mirror was 35 meters away, and he used an 8-sided mirror, and he needed to spin it at 32,000 revolutions per minute to make that cycle. So here's your octagonal mirror. And here's your mirror. Blah, blah, blah. And here we go, the light, green light. The wavelength of about 500 nanometers hits there. Goes your 35 kilometers, hits there, and then here's your eye, and you see it. Okay, and the mirror is turning at 32,000 RPM, revolutions per minute. So what we have to do, if the mirror is turning at 32,000 revolutions per minute, what we have to do in this case is find out how long does it take for the mirror to make, it's an 8-sided mirror, so how long does it take the mirror to make 1/8 of a turn, 1/8 of a turn, or 1/8 of a cycle? Because when it makes 1/8 of a cycle, in other words, it hits here, and then this portion of the mirror has now moved to here, that's 1/8, right? And then so the mirror, since the mirror is symmetrical, it will have exactly the same orientation. If it makes 1/8 of a turn, the mirror will look exactly the same. Or sorry, not the mirror. The mirror. The 8-sided mirror will be in the same orientation. If it makes 1/8 of a turn. If it made a quarter of a turn, it would be in the same orientation because of its symmetrical mirror. So there's our goal. Our goal is to find out how long does it take to make 1/8 of a turn. And then we just use this formula here, because we know that the distance the light has to travel. If it's 35 kilometers, it has to go 35 kilometers this way, 35 kilometers this way, so it's 70 kilometers. And the fact that it's at an angle is totally negligible. This angle here, of course, you can say, well, if this is 35 kilometers, then this distance here is obviously a little longer, but it's very negligible. We're talking about a small mirror at a huge distance, so we're just going to go with 70 kilometers, even though theoretically it's going to be slightly more than 70 kilometers. So velocity equals 70,000 meters. So we get a number from it, divided by the time. And again, we have to find out how long does it take the mirror to make 1/8 of a turn. And this is the way, there are many ways you can do this. This is just the way I do it because I'm more from a math background. And so I'll do it with a ratio or a proportion. And I will say that if something makes 32,000 cycles per 60 seconds, that's revolutions per minute, then how long will it take to do 1/8 of a cycle, or 1/8 of a turn, 1/8 of a revolution, whatever you want to call it? You could put this as revolutions, if you want. And then you just cross multiply and divide. 32,000x. 32,000x equals 60 divided by 8. X equals, where's my calculator? X equals 60 divided by 8 divided by 32, 123,000 equals 2.34 times 10 to the negative 4 seconds. And of course, you're going to get a very small number. This thing is going 32,000 around 32,000 times in a minute. So to make 1/8 of a turn is going to be a very small number. And then, oops, I made a big mess as usual. Let's rewrite this whole thing. Velocity, the velocity of the speed of light equals 70,000 divided by 2.34 times 10 to the negative 4. And there's your calculator, 70,123 divided by the answer, and you get an answer of 6.7 meters per second, which, if you round off, is 3.00 times 10 to the 8 meters per second. And the actual speed of light is slightly slower than that. It's not exactly 3 times 10 to the 8 meters per second, but that's pretty darn close. So that's a Michelson experiment. It's brilliant. And that was more than 100 years ago, and we have more accurate answers now, but the answer that he got was pretty darn impressive. Example number 2 says if the sun were to blow up right now, determine how long it would take before we saw the explosion here on Earth. Easy question. Time, we want to calculate the time. Time equals distance over velocity. And of course, we have to know the distance between the sun and the Earth. Oops, do I know that? I know it. I think it's 1.5 times, it's 1.5 million meters. Million kilometers, 1.5 times. Okay, now we have to go to Google because I don't want to stop and redo this entire lesson. That'd be kind of tragic. Hello, McFly. Distance from Earth to Sun. Yeah, is wow, look, you checked it out, 150 million kilometers, 150 million kilometers. So let's go back to here, 150 million kilometers. So 150 times 10 to the 9 meters, because that was 150 million kilometers, so that would be times 10 to the 6. And we want it in meters divided by the velocity. 3 times 10 to the 8 equals 150 E9. I should have done this beforehand. Divided by 3E8 is 500 seconds divided by 60 equals 8.33 minutes. Okay, that's a pretty easy question. You're unlikely to get that on a diploma, but it has some value. And that is it. That is the end of the speed of light. Hope you appreciated how physicists and scientists tried to make this monumental calculation and how important it is. See you soon.